Hello, hello, Algebra 1 students, and welcome to your last lesson in Topic 8. Yep, we finally reached the end of our factoring polynomials unit. I know it's been a long ride, but hopefully it's been worth it and you feel pretty comfortable with factoring. The last day of this unit is just going to focus on two more special cases of quadratics. Remember, last class we discussed the case where you had a greatest common factor and you needed to factor that out. And then we also discussed the case when a was 1 and we had to go through, or we were able to go through and factor without a box. Well, again, today we'll conclude with two more special cases where we won't need to use the box, at least on one of them, maybe on both. But in order to get there, we need to remember what we learned in 8.04, which was multiplying two special cases. And yeah, today we're just going to work backwards from those. So the two special cases that we need to remember are perfect square trinomials and also a difference of squares. So you have 6 problems here, and your goal is to multiply them out so your final answer should be in standard form. And you want to decide if that problem represented a perfect square trinomial or a difference of squares. So good luck multiplying each of these. If you need any hints, you can always unpause. So good luck, and we will come back together in just a couple minutes. Ready, set, go. All right, you're back. Well, there are a few things we needed to remember. First, on part A, or problem A, we needed to make sure that we did not distribute the square, right? We learned a few times now that that kills puppies and nobody wants that to happen. You're not allowed to distribute a square or a square root if there's any addition or subtraction. So instead, we need to go through and remember that we can write this problem as x plus 3, and a square means something times itself. Okay, and so now all we need, I think, is to organize our box. And you don't need the box. I'll do a couple with and a couple without the box here, just so we can remember how to do that, and multiply everything out. Okay, so we have x times x, that's x squared, 3x, another 3x, and remember 3 times 3 is 9. So we multiply to find the insides of the box, and then if there are any like terms, and there are here, we add those together. So 3x plus 3x gets us 6x. And then there's the positive 9 at the end. So here's our final answer. Then we had to decide if this was a difference of squares or a perfect square trinomial. Well, if we think about this box, the outsides of the box are exactly the same, which means the length of the outside of the box is the same on each side. And what do we call a rectangle where the lengths are the same on each side? We call that a perfect square trinomial. And so this is indeed a perfect square trinomial. Okay. Our second one looks like it's already set up just fine, so I think we can do our box method here, nothing too bad. X with a plus 3, x with a minus 3, so we have sides that are not the same. One's 3 long, one's 3 short, but we can still find the interior. X squared minus 3x, positive 3x, and negative 9. And then when we combine our like terms, when we do 3 plus negative 3, we should see those cancel. So that makes 0x's minus 9. And we should realize that even though that's in standard form, most people don't write the 0, so x squared minus 9 would be our final answer. Looking inside the box, x squared is clearly a square, right? We can think back to those blue square algebra tiles. It's also x squared. It's bordered by x and x. And then 9 is also a square. It's had 3 tiles and 3 tiles on each side. Now you might say, well, wait, one's a 3, one's a negative 3. That's true, but if you just take 3 times 3, you ignore the negative, you get 9. Now we have a square, and a negative in the middle means a difference between two numbers. A difference means subtraction, and so this answer is a difference of squares. Okay, hopefully you're getting the idea, but let's try another one over here with part C. We have 2x. I'm going to give myself a little bit more space here. 2x minus 1 times 2x minus 1. I'm going to do this multiplication without the box. It's good practice. It's how I normally multiply, honestly. So 2x times 2x is 4x squared times negative 1 is negative 2x. And then we have another negative 2x, and a negative times a negative is a positive 1. Okay, and then we go through and combine like terms. 4x squared, negative 4x, and a positive 1. We need to recognize when you multiply something by itself, the answer it creates is known as a perfect square trinomial. Something else to notice is that 4x squared is actually the same as 2x with a square, And this 1 right here is the same thing as 1 with a square. In fact, you'll notice that's pretty common when we do the next couple problems too. Okay? So here's our next one. I'm going to skip the box for now. I'll use the box a bunch today, but I figure might as well remind you that there are other methods to do as well. 4x times 4x is 16x squared. 4 times 5 is positive 20x. Then we have negative 5 times 4, which is negative 20x. And finishing this off, negative 25. We should realize that the negative 20 and positive 20 will cancel, and it leaves us with the answer of 16x squared minus 25. And again, note that 16x squared is actually the same thing as 4x times itself. We did that at the beginning, right? And then 25 is the same as 5 times itself. And look at that nice difference of squares right there. All right, 2 to go. 3x plus 2y times 3x plus 2y. As we go through and multiply, we'll need to be a little careful here, and you'll see why in a second. That's 9x squared, nothing bad. When we do 3x times 2y, we can multiply the 3 and the 2 to get positive 6. But then x times y aren't like terms, so they're not going to combine, so we just keep it as x times y. However, no one puts that extra dot, so we just keep it like this, so 6 times x times y. Now if we look at our next one, 2x times 3y, again 2 times 3 is 6. And then you might say, well, it's y times x, so wouldn't that be yx? Well, yeah, it is. However, traditionally in math, we write our answers and our terms in alphabetical order, and since x comes before y in the alphabet, we write it as xy. That also allows us to see like terms a little bit easier, which we'll come back to shortly. But 2y plus 2y, 4y squared. Okay, so combining like terms, 9x squared, you have 6 of these xy's, and you're getting 6 more of them, which means we have 12 of those xy's. See how it's easy to see the like terms there, 6 of something, 6 more, and then plus 4y squared. Again, you can notice that this 9x squared is the same thing as 3x squared. We have this term in the middle, and then 4y squared is the same as 2y squared. Right? You can even see that connection to the original problem. Okay. This is, again, a perfect square trinomial. I imagine at this point you can kind of tell when it's going to be a perfect square trinomial versus when it's a difference of squares. Right? If you look at this one, the two binomials we're multiplying are different. They differ by a negative. I think that's going to make a difference of squares. And I think that's going to happen. I'll erase this to give myself a little bit more room, because 6 times 6 is 36. X squared times x squared, don't forget, x squared means x times x. The other x squared means x times x. And we're multiplying them together. That gives us x to the 4th. Okay, but when we do 6x squared times 2y cubed, that's going to give us 12x squared y cubed. The negative then comes into play, because when you do a negative 2 times positive 6, that's negative 12 x squared y cubed, right? When one is positive and one's negative, you're going to end up getting those two middle terms to cancel out. And in fact, the shortcut that we talked about when we first multiplied these is you actually only needed to multiply the first two terms and then multiply the last two terms. And this is going to give me negative 4 y cubed times y cubed. Same logic here. We add the exponents, y to the 6th. We only needed the first and the last term because the two terms in the middle always cancel in a difference of squares. So 36x to the 4th minus 4y to the 6th. And notice we could again rewrite this as 6x squared squared minus 2y cubed squared. Right? We just take the original terms inside those binomials, add squares, and we can see that difference of squares. All right, hopefully you whipped through that a little bit faster than I went through it. It's a nice review for you, though, especially since you have a test coming up. And the first half of your test will be multiplying like we just did. Right? That's what we covered for the first 4 or so lessons. We added, subtracted, and multiplied polynomials. So we also have named these patterns before. Let's look at them quickly just to make sure we're comfortable, and then we will move on to working backwards. All right, x plus y squared. I don't have enough room to use the box, so I'm just going to write this out. I'll probably need 2 lines worth of room here. X plus y squared becomes x plus y times itself. That means that the answer is going to be a perfect square trinomial. And I know it's going to be a trinomial because there's no negative here. I'm almost going to eat those words in a second, but there's no negative, which means nothing can cancel out. So we get x times x, that's x squared. We get x times y, that's xy. Y times x, we write in alphabetical order, that's xy, and y times y is y squared. When we combine like terms, we need to realize there are invisible ones in front of these, so my standard form will be x squared plus 2 of those xy's plus y squared. You can throw parentheses here if you want. All right, nothing bad. Perfect square trinomial. Now we get to the x minus y squared, and I have students get this difference of squares stuck in their head, so they say, okay, x minus y squared, that's going to be x minus y times itself, so I only need to multiply these first two, these last two, and we're done because the negative will cause things to cancel out. Well, that's not the case here, right? This is something times itself, and anytime that happens, we call that a perfect square trinomial. You might be asking, well, wait, why doesn't anything cancel out? Well, let's investigate that. We have x times x, that's x squared. X times negative y is negative xy. Negative y times x is again negative xy. And negative y times negative y is positive y squared. Notice here we actually end up having two negatives because these are both negative. You're not going to get that negative positive split from before. So when I put the ones in front, we see that this is actually x squared minus 2xy plus y squared. There's our perfect square trinomial. And they only differ here by one has a plus, one has a minus. Right? They both end in adding squares. Comparatively, this last problem, now we have one positive, one negative. So we end up with x squared minus xy plus xy, there's that plus minus combo, minus y squared. They cancel. Our standard form will be x squared minus y squared, and this is a difference of squares. Okay, so here's our review. Let's look into our shortcuts for the day. Although we just focused on multiplying on that first page, the second part of this unit from 8.05 and up has been factoring. You could also say dividing, but factoring is a more correct term here. Factoring polynomials. Our first exploration today is going to involve factoring a difference of squares. Right? So that means that our standard form polynomial given to us, right, our standard form right here given to us will be that x squared minus y squared. Or for most of the first part, it's going to be ax squared. There are 0 x's minus c. Right? So we simplify this as ax squared minus c. If that looks a little confusing, right, we're actually going to see some nice examples down below, but it's really saying something like this. X squared minus 9 is the same thing as 1x squared plus 0x minus 9. There's that ax squared plus bx plus c we covered last class. Right, so most of what we're going to have to factor is going to look like this. There might be some exceptions, which we'll see shortly, but generally it looks like this. Our goal, when we're given something like this, will be to put that polynomial into factored form. The factored form of a difference of squares is given as ax plus b, and it'll be times ax minus b. And we learned in the past that two factors that are identical, with the exception of a negative, are known as conjugates. Sometimes you hear them called conjugate pairs. Right? Here are conjugate pairs because they're identical, but one is positive, one's negative. So they're not exactly identical. So there are 3 problems down below for you, and your goal is to factor them. Now, if you need to use a box, use a box. There's nothing wrong with that. And then we'll discuss if there's any sort of shortcut. So, 3 problems for you, A, B, and C. Let's see what you guys can do. Your final answer should have 2 sets of parentheses, just like so. Ready, set, go. All right. Well, if I wanted to factor this using a box, I don't think it's too terrible, right? We have our x squared, we have our minus 9, we need 2 numbers that add up to be 0x, and also 2 numbers that multiply to equal first times last, negative 9x squared. Focusing on the multiplying using your factor sheet, I think this will be positive 3 and negative 3. That makes negative 9, and 3 minus 3 is 0. When we're factoring the outside of the box and you have this x squared, the only thing they can have in common is an x. That's got to be x and x. X times 3 is 3x, x times negative 3. And so my factored form is that x plus 3, x minus 3. That fits our pattern from the difference of squares from the first page. We're doing just fine. Now, you might have noticed that actually this x squared here has a 1 in front of it. And so I think we can actually skip the box here, right? We can think of this as 1x squared plus 0x minus 49. We can ask ourselves, what will split up the 0x and multiply to make negative 49x squared? This is the shortcut we learned last class in 8.10. And I think with that 0, we need to have the same number, 1 positive, 1 negative. What times itself is negative 49? Well, I think that's negative 7x and positive 7x, like so. And because there's a 1 in front, we can skip right to our answer. X with a positive 7, x with a negative 7. But then disaster strikes for part C in a couple ways. First, you might realize this is not in standard form, so I'm going to rewrite that quickly. And second, you might realize that this negative 16, or sorry, the 4 that's out front of the x squared means we can't use that shortcut from B. Or can we? Isn't there a greatest common factor to all of these? We can skip the 0. There wasn't actually the 0 in the first part. What's common to 4 and 16? Well, if you said, well, 4 is common to 4 and 16. 4 divided by 4 is that 1 we're always looking for. 0 divided by anything is 0, minus 4 at the end. So we have two numbers that will need to split up the 0x, and two numbers that need to multiply to make first times last, negative 4x squared. Okay? Again, this will be a negative 2, positive 2. Hopefully you guys see what's happening pretty much every time. It's the same number. And so I can say x minus 2 and x plus 2. But if you multiply this out, it doesn't equal the starting one. No, it doesn't. We need to take the 4 that we divided out of everything, and then we're good. All right, so I mentioned today we're looking for shortcuts, even more shortcuts than we've already seen. Each of the following problems, the original problems, can be written in the form of a squared minus b squared. Let's prove that quickly. Right, x squared minus 9 can be written as x squared minus, what squared is 9? Isn't 3 squared 9 because 3 times itself is 9? Okay, x squared minus 49 would be x squared minus 7 squared. And 4x squared minus 16, this one's always tricky because people forget the 4. We don't just want to say 4x squared. We want the entire first thing to be squared. So I think that needs to be 2x squared minus 4 squared. Now, being able to do that, being able to see that 3 times 3 is 9, and all that fun stuff, and 7 times 7 is 49, does that give us a hint of what the answer is going to be? Well, if you look at the answers, notice that 3 and 3, 7 and 7, and I wrote 4 here, and that one is a little bit different because I think I forgot to divide out the 4 here, so let's see what that looks like. Right? I took the 4 out first, so it was x squared minus 4. Then it would become 4x squared minus 2 squared. And I think we match over here now too. 2 and 2. So if we wanted to write a general rule to factor a binomial of a squared minus b squared, then I think all we would do is we would put our two sets of parentheses. One has a positive, one has a negative. Whatever this a thing is that's being squared will go in the beginning, and b will go at the end. Now, we should probably figure out how to use that quickly, so I have 9 problems here. Notice that you don't have a lot of room for work because you don't need to show a lot of work. So, let's see if we understand why. T squared minus 25. Well, I know how to factor this right away. Can you see how? T squared means we're going to start with t and t, because t times t is t squared. To cancel out the middle terms, we need one positive, one negative. We know in a difference of squares, the numbers that go in the end have to be the same number. So the question we might ask ourselves is, what times itself is 25? And I bet you could probably all think, oh, 5 times itself is 25. Now, think about what we did to get from here to here. And what I'm asking you to think about is, what can I do to t squared to make it equal t? And what can I do to 25 to make it equal 5? Many of my students said, oh, 25 to 5, you divide by 5. And you're right. But if you do t squared divided by 5, does it become t? Think about how these are related to the original squares. They're related because if you take this and multiply it by itself, you get the original number. Multiply this by itself, you get 25. And what's the symbol that we can put around a number that looks for a number times itself? You remember it from last unit? Isn't it that cool little check mark, that square root symbol? And so you'll notice if you do the square root of each of these, it's actually going to give you the starting number and the ending number. Just don't forget the plus minus to make it a negative at the end. So knowing that, why don't you guys go through and try these other 8? They should go pretty quickly. I'd say maybe 2 or 3 minutes total. No box necessary. We're practicing that factoring a difference of squares. Ready, set, go. Okay, you're back. I'm just going to quickly tackle a few of these. I'll demonstrate a few becauses, but not all of them. I imagine you can do those. But factored form first, x and x. That's the only way that makes x squared. 1 positive, 1 negative. You can put the negative first. That's fine. And I think 10 times 10 is 100. That's it. Okay. 4x squared minus 9 is a little trickier because we need to look at the square root of 4x squared. And we also need to look at the square root of 9. The square root of 4x squared, what times itself is 4x squared? We need a 2. 2 times 2 is 4, and an x. Square root of 9 is 3. So I think my factored form here will be 2x times itself to get 4x squared, plus minus. And 3 times 3 is 9. Okay, let's keep working through. 4 minus b squared. Notice the negatives on the b squared this time. So I think we need a positive 2, that makes 4, and a negative b, positive b to get the negative b squared. X to the 4th minus 4 can be a little trickier, but my students did really well with it. They realized that we needed to multiply to make x to the 4th, and they said, well, that has to be x squared. X squared times x squared is x to the 4th. I'm going to switch it up. I'll do the negative first because I'm a rebel, though I did it first last time too. And 2 times 2 gets you 4. Part F, x to the 6th minus 25 looks really tricky. However, using the same logic as x to the 4th, I bet you can see this is going to be x cubed times itself, and then 1 positive, 1 negative. 3 to go. 16h squared minus 36k squared. Here we go, here, 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 here. I found my students were good with the 16h squared. They said 4h and 4h times itself is 16h squared. And they were good with the 36. They said 6 times 6 is 36. However, several of them forgot the k squared. We also need k's on the 6's. So when we do 6k times 6k, we get 36k squared. Moving on through. 25x squared minus 49y squared. I think you get the idea now. 5x minus 7y. 5x plus 7y. And our last one, 36x squared minus 121y squared, 6x minus 11y, 6x plus 11y. Okay. At this point, you are ready for what is arguably my favorite math song to show this year, and what is arguably one of the most famous math songs out there. At the time of recording, the video that I'd like you to watch has about 1.5 million views. It was done by a high school about 10 years ago, maybe a little more than that, I think in 2010. And it's super catchy and fun. It's only about 3.5 minutes of your time. So if you haven't watched it yet, please go ahead, look it up on YouTube, the Teach Me How to Factor song. It is a little cringeworthy, but it's high school students making a hilarious math parody song. So take it with a grain of salt, have fun, laugh, and at this point you should be able to understand everything that they discuss in the video. Plus they'll teach some things in slightly different ways, so you never know, you might actually learn something. Go ahead, pause this, watch that. Once you're done, unpause and we'll tackle the last part of today. Ready, set, go. And you're back. All right, let's move on to our third page. Now, these perfect square trinomials are honestly a little bit harder to recognize. Some of you might recognize them. I imagine most of you, though, are going to focus on the box. There's a way that you can rewrite these and use that pattern that we discussed on the first page a little bit more in depth, but I'm not going to go into it this year. If you guys are curious, just let me know, and I'm happy to make you a short video on how to do it. But either way, there is something interesting with the answer, so I think it's still probably worth going through these. You'll probably end up using a box most of the time. Not all the time, but most of the time. So here we go. Remember that a perfect square trinomial was always going to factor to x minus y squared or x plus y squared. We haven't really seen too many answers that look like this yet, so they're probably worth discussing. Okay, this should say if you can recognize an expanded trinomial as a perfect square trinomial, then that can save you some time. So recognition can be the tough part, but what you're really looking for to recognize is that this first thing can be written as something squared. That's pretty easy. And this last thing is also something squared, right? 9x squared will be 3x with a square, and 1 will be a 1 with a square, and so on and so forth. But you don't always think to do that. And there's something special that has to happen in the middle that we're not really going to cover this year. So again, you can take it with a grain of salt, but assume that most of these, if not all of these, are perfect square trinomials. So let's see how we actually factor. This first one has a 1 in front of it, so we can just skip right to our shortcut. We need to split up the 8x, and we need to multiply to make 16x squared. The nice part with perfect square trinomials is because it's something squared, that number at the end is going to be what multiplies to make it and what adds to make the middle. So that's pretty easy, right? Did you notice how I put those basically together? And so what we can end up with then, skipping straight to our answer, is going to be x with a 4 and x with a 4. However, don't forget that this is not what the answer is going to look like on a test, because on a test they always try to write the least possible, and you can write this in a more simplified form. X plus 4 times itself will be x plus 4 squared. All right, let's look at this next one. Now this next one, we don't have the 1 in front, so instead, why don't we go ahead and make a box and remind ourselves of how this works. 9x squared with a 1, we need to split up the negative 6x and multiply to make 9x squared. Again, once we get here, this is going to be the giveaway, right? If you take a look at these, this is going to be a 3 and a 3. However, 3 plus 3 isn't negative 6, so we know at least one of them has to be a negative, but to multiply to make a 9, I think both have to be negative. A negative times a negative is a positive. So negative 3x, negative 3x, and then we find our outsides. Again, this should be pretty easy. To make 9x squared, it has to be 3x and 3x. It has to be this guy up top. And then minus 1, and minus 1. The sides have to be the same. So once you have one side, the other is the same as well. That's where our square comes in. And so our answer, instead of writing 3x minus 1 times 3x minus 1, is just 3x minus 1 squared. Okay. This next one is nice. We just have the 1 in front of the x, so we know these two numbers have to add up to split negative 16x, and they have to multiply to equal 64x squared. However, realizing the 64 is 8 squared, that's going to probably tell me I need an 8x and 8x. So it saves you a bunch of time from having to look up your factors. And then because there's a 1 in front, can you see what we can skip to for our answer? It's got to be x. Oh, wait, this is a negative 16, huh? They both have to be negative. For a perfect square trinomial, either they are both positive or both negative. So 3 done. Let's keep on skipping through. 25x squared, 10x, and 1. Well, I think maybe we'll use the box here. We have that 25x squared and 1. Two numbers to add to make 10x, and they have to multiply to make 25x squared. What plus itself is 10? What times itself is 25? Well, those have got to be 5x and 5x. And again, we could see that by saying 25x squared is 5x squared, and 1 is 1 squared. This gives us 5x and 5x. And you'll find on the outsides it has to be 5x and 5x. with a 1 and a 1. So 5x plus 1 squared. Pretty quick, right? Now, E presents a particular type of problem where E says we need two numbers that are going to split up 24, which doesn't seem too bad, right? It has to split up 24x, but then it has to multiply to equal whatever 16 times 9 is. Now, I haven't done this yet, but I am pretty convinced I can do this one quickly, because to add to make 24 with a perfect square trinomial, these guys will always be the same number. So even though we normally start with multiplication, do you know what plus itself is 24? I bet this is 12x and 12x. And now we can actually do 16 times 9 just to double check. 6 times 9 is 54. 9 plus 5 more is 144. And so this should have been 12x times 12x. Right? That was pretty nice here. Now, figuring out the outsides can be tricky, except with this perfect square trinomial, this guy right here can be rewritten as 4x with a square, and 9 can be written as 3 with a square. So my guess is this is going to be 4x with a plus 3 and 4x with a plus 3. And checking my bonus box, it does seem like we did it correctly. So 4x with a plus 3 squared. Finish off with our last one, x squared plus 4x plus 4. I think this will again be a perfect square trinomial, x with a square, 2 with a square, but we should probably double check. We need to split up the 4x and also multiply to equal 4x squared. Does 2 work? It does. 2 plus 2, 2 times 2, and so my final answer is x plus 2 squared. So there's our perfect square trinomial rundown. Nothing too awful. To really conclude our factoring, and I have a couple bonus problems on the next page, but to conclude our factoring, I have 6 practice problems at the bottom of this page, and they each need to be factored. Now, each of the 6 is going to use a slightly different technique. Now, if you don't like these techniques, can you go through and use the box every time? You betcha. You can use the box every single time on these. However, again, if you don't want to, I think you really only need the box on probably one of these problems. No, probably 2 of these problems, actually. But let's go ahead and see what we can do. I'm excited to see our success. You guys should be able to work through these and then unpause and skip to any of the ones you had trouble on. Ready, set, go. All right, we're back. Okay, first one, 1 in front of the x squared. What plus what is 6? What times what is 8? That's got to be 4 and 2, doesn't it? 4x, 2x, 4x, 2x. And because there's a 1 in front of the x squared, we know our answer will be x plus 2 times x plus 4. What did that take? 15 seconds? Not bad. All right, second problem, there's a number in front of x squared. So the first thing I'd say is there a GCF for all 3 terms? Can we simplify the number in front of x squared? Sadly, there is not a GCF through all 3 terms. So I think this is our just basic box method, which hopefully we're fairly talented at by this point. We need to split up the 14x, the negative 14x in the middle, and we also know that that's going to multiply to make a times c here, which is 24x squared. Okay, so to do that, we're going to end up with, what does that look like? Maybe 12 and 2, I think. 12x and 2x, 12x and 2x, but it needs to add to make negative 14 and to multiply to make a positive. Both have to be negative. Negative 12x, negative 2x. Let's find our exteriors. 12 and 8 each have a 4 in common, I think. And that makes sense because 8 and 2 each have a 2 in common. 4 times negative 3, 2 times negative 1. And we have our final answer. 4x minus 1, 2x minus 3. Okay, part C, we might initially look and say, there's a 2 in front. Drat, we can't use the shortcut from A. But isn't there a GCF here? I think if you look at these 3, they all have a 2 in common. So I'm going to go through and factor out or divide out the 2 to leave me with 1x squared minus 1x minus 12. And I think then we can do our nice shortcut here where we're just splitting the negative 1x from the middle. We're multiplying to equal the first times the last here. And this looks to me like it's going to be negative 4x and positive 3x. Looks pretty nice. And so then I think we can skip right to our answer. That was 1 when in front of x, so the only way to make 1x squared is x times x. x minus 4, x plus 3, and don't forget the 2 that's still hanging out front. Fourth problem. Fourth problem has that negative 18x squared plus 3x plus 3. I think probably the very first thing I'm going to try and do here is I'm going to look for a GCF, and I think there is one. I think if you look at all of these, there's a 3 in common. Now, just me being particular here, I always like x squared to be positive. You don't have to make it positive. But I'm going to divide everything by negative 3 because I know a negative divided by a negative will give me a positive. This becomes a minus 1x and a minus 1. I think this would probably be easy enough to guess and check to factor, so I'll remind you of how to do that. To guess and check to factor, and you could use a box here, nothing wrong with it. I know I have to multiply to make 6x squared. There's only 2 ways to do that. There's 6x and x, or it could be 3x and 2x. And again, I don't know which one it is, so I think this is good for us to check. My guess is it'll be the 3 and the 2, just because this number is pretty close to 0, and these are pretty close to each other. But let's check this one first. So to multiply to make this negative 1, it's either positive 1, negative 1. That's negative 6 plus 1. That's negative 5. That doesn't match my middle term. If you switch them, negative, positive, that is 6 minus 5. That also doesn't match the middle term either. So I think this guy's out. But if we try this one, this is negative, so I think the bigger one should end up with a negative. That's negative 3x, and that's positive 2x. Negative 3 plus 2 is the negative 1 we get here, and there's my guess and check. Now you could argue, well, you could just use the box here, and you're right. You can always use the box. I will tell you that 95% of the time, maybe more, I tend to not use the box. It's faster for me to guess and check. But I know some other teachers and some other students that love using the box, and that's fine. All right, E should be easy. This looks like a difference of squares to me, right? So I think we're just going to skip straight to our answer. It's got to be x and x to make x squared. 81, the square root of 81 is 9, so x minus 9, x plus 9, Shazam. And our last one, 3x squared minus 48. This one could throw you off right away, because if you look for the square root of 48, or the square root of 3, they're not nice numbers. But wait, isn't there a GCF in here? I think we can divide both of these by 3, and that will give me x squared minus, let's see, 48 divided by 3 is 16, isn't it? And so now isn't this an easy difference of squares? This will be x times x to make x squared. What times what to get 16? It's got to be 4. And we're set. Okay, well, hopefully you felt all right on most of that. This last page here is really just some kind of bonus stuff, some extra practice for you. So I'll go through it, but I think most of you will probably pause the video now because you guys are doing just fine. But if you want to get some extra practice, get a little bit better at factoring, please stay with me. So let's go ahead and see what we can do. Our first extension problem, Mr. Grant gives a quiz. He asks the student to factor 16a to the fourth minus 100a squared. He has 5 students, Osvaldo, Sierra, Nikki, Holden, Wyatt, and Melanie. By 5 students, he means 6. They all get different answers, and actually you can see their answers down below. When Mr. Grant actually grades their tests, though, he does award full credit to each of his students, which means they all did it correctly. Okay, so for part A, I would like you please to go through and figure out how each student got to the solution. It's important to be able to read through other people's work. And then once you've done that on part B, decide which one you think is the most correct. All right, so let's just start at the top. 16a to the fourth minus 100a squared. Let's see what happens here. It looks like they factored out, Osvaldo's factored out a single term. It looks like you took out a 4a squared. So maybe if you thought about like that box right here, we had 16 and then 1, 2, 3, 4, and then negative 100, 1, 2. And it looks like Osvaldo realized there were 2 a's in common, so we took out an a squared. And then he said, well, what's common between 16 and 100? I think 4 is in common to both of those. So he divided both of these by 4. 100 divided by 4 is 25. And then he took the leftovers. Right? The leftover here would be an a squared. And look, we got 4a squared and 4a squared minus 25. Looks like he did factor this, didn't make any mistakes, took out an a squared. Right? It looks like there's nothing else in common here. Okay? What about Sierra? Well, it looks like Sierra pretty much did the same thing too. I think Sierra took out an a squared from both of those, same way that Oswaldo did. And then she also divided everything by 2, right? And if you divide everything by 2, that'll be 8a to the fourth minus 50a squared. And that is technically correct. She was able to factor out a variable, a squared. She didn't take out the greatest common factor, so I think Oswaldo is probably a little better than Sierra's here, but she's not wrong. All right, third problem. Let's see. It looks like Nikki has 2 sets of these parentheses here, and it looks like they fit a difference of squares. So can we do that? Looks like we're here and here. I think if we go through and we look at the square root of 16a to the fourth, I think that is certainly 4a squared, because 4a squared times itself is 16a to the fourth. And same thing, the square root of 100a squared will be 10a. So minus plus looks like minus 10a plus 10a. Yeah, I think Nikki utilized that difference of squares pattern wonderfully. All right, let's keep moving on then. This one went weird, didn't it? Well, actually, this one to me reminds me a lot of Nikki's. I'm actually going to steal Nikki's answer and jump down to Holden's over here, where we had 4a squared minus 10a, and then 4a squared plus 10a. What was similar? Well, I actually see a 4a squared minus 10a here, so I don't think I need to do anything with this guy. It's all involved with this piece that's different. Do you see anything in common here, though? I think 4a squared and 10a both have a 2 that we can divide out. And if you divide the 2 out, this becomes a 2, this becomes a 5. And they both have an a in common. I should have left more space. If you take an a out of each of them, instead of a squared, we're just left with a. And if you remove the a from here, there's nothing at all. Can you see that 2a times 2a is 4a squared, and 2a times 5 is 10a? And so I think Holden's last part here, here's your 2a, here's your 2a plus 5, and here's your 4a squared minus 10a. Holden's is also correct, and arguably his is the most simple so far. The reason I'm saying Holden's is the most simple is because there's a 2a plus 5 and a 2a over here, where a is to the first power. Ideally, when we factor, fully factored form should have each variable to the first power. And so, although maybe it's not perfect yet, I think Holden's doing pretty well. Let's go ahead and take a look at Wyatt's, though. I think Wyatt's is, again, very, very similar to each of these. I'm going to again borrow Nikki's answer, where we had 4a squared minus 10a and 4a squared plus 10a. And you can see it's very similar to what we have down below. I'm going to again factor out that 2a from this second set. That'll leave you with 2a plus 5. But then I'm going to do the same thing for the first set. I'm going to factor out 2a here, and that will leave me with 2a minus 5. Right? Double check by multiplying back in that I haven't done any crazy black magic. And then, because this is all attached by multiplication, we can multiply 2a and 2a to make 4a squared out front, 2a minus 5, and 2a plus 5. In fact, this is probably as simple as you can go, at least so far. Our factors all have a to the first power. Technically, this isn't in the parentheses. A squared, though, could be written as a times a if you wanted. Right? You could do individual parentheses there, but generally, if it's just a single letter, we keep it as a square. All right, last one. Melanie. 4a times 4a squared minus 25a. Well, it looks like if we jump back to the box over here, we have 16 and then 1, 2, 3, 4 a's, and 100, don't forget that negative, a times a. It looks to me like Melanie did 2 things. First, she realized that there's an a in each, so she factored that out. And then second, it looks like she realized that 16 and 100 can each be divided by 4. So that leaves you with a 4, and that leaves you with a negative 25. And then she said, well, I've got some extra a's, so here's an a cubed, and here's an a. And that does seem to match down here. I would argue that Melanie's is probably the least simplified because she still has an a cubed as a factor. Right? These guys have your a squareds, but I think really our most simplified is going to be Wyatt's out here with 2a minus 5, 2a. plus 5. So hopefully that gave you some practice of both using a GCF and the difference of squares. Let's get to our very last problem for the day. A rectangular pool has an area in square feet of 8x squared plus 26x plus c. One of the sides of the pool is represented by the expression 2x plus 5 feet. Let's go ahead and label this first. So we need a picture of this scenario, okay? I'm going to go ahead and just draw my pool over here. We know the entire inside of the pool is 8x squared, this is the area, right, plus 26x plus c. And we know one of the sides of the pool is 2x plus 5. Well, if we know one side, we also know the other side. But I don't seem to know the top or the bottom yet. Okay? So the first thing says, find the width of the pool in terms of x. So we know the length, but we don't know the width. Well, how do we do that? Well, basically what they're telling us is that we are going to do 2x plus 5, that's the length, times some width. And my answer is going to be the area, 8x squared plus 26x plus c. Doesn't this seem kind of like this box method and the factoring we've done so far? Let's try to fill everything in here that we can. Right? We've got this right here. I'm going to split this into 4 pieces. I know the 8x squared and the c go in here. I know this has to be a 2x and a 5. Does that give us enough to find everything? Well, we know this is 2x, so I think this one has to be, up top, has to be a 4x, doesn't it? 2x times 4x is 8x squared. And then check this out. 4x times 5 means the inside has to be 20x. And why is that helpful? Well, it's helpful because these two blanks have to split up what? They have to split up the 26x that's up here. So if I know that's 20x, do I know this blank space? 20x plus what is 26? Well, yeah, 20x plus 6x. And so, can we finish this off? 2x times what is 6x? 2x times 3 is 6x. So just by knowing how this box has to be formatted, we were able to reverse engineer the other side of the pool, which is a pretty darn cool problem. So when they want the width of the pool, that's going to be 4x plus 3. All right, let's look at part C. Find the value of c in the expression 8x squared plus 26x plus c. Oh yeah, we didn't find c yet. But that's our bonus box, isn't it? 5 times 3. That means that c was 5 times 3, which is 15. So in fact, we can really complete this whole thing. We know we had 2x plus 5 initially, and we found the top of the box, which I did in purple, has to be 4x plus 3. And I know multiplying this out, my answer was 8x squared plus 26x plus 15. Awesome! All right, given that the length of the pool is 25 feet, find the width and the area of the pool. Okay, well, let's start with the length. The length of the pool, right, is given to us as 2x plus 5. So, but they also told us it's 25. So which one is it? Well, it's both. So we know that 2x plus 5, the length, is actually equal to 25 feet. And I think that's something we can probably solve, isn't it? Subtract 5 from each side gives us 2x equals 20. And we divide by 2 to find that x equals 10. Well, now that we know that x is 10, I think the rest falls into place. To find the width of the pool, well, we know that the width was given to us as 4x plus 3, right? But now we know what x is. X is 10. And so, through PEMDAS, we get 40 plus 3, which is 43. Last but not least, they asked us to find the area. And there are actually 2 ways to do this. The first way is we know that the area was 8x squared plus 26x plus 15, and we know that x is 10. So you could go through and you could substitute 10 in for your x. 10 squared plus 26 by 10 plus 15. And you've got quite a bit of math to do here. I'm trying to run out of room. I'll use the bottom of the page. PEMDAS says do the exponents first, so that's what I did first. Then do the multiplication, right? And I'm just doing some quick mental math. Multiplying by 10 is pretty easy, isn't it? And then do all the addition. This is going to give us 1060 plus 15 more is going to give us 1075. However, don't forget, to find area of a rectangle, isn't it just base times width, or length times width? And we know that the length is 25, and we know that the width is 43. And I think you'll find if you multiply all of this out, you should end up with 1075. Ta-da! So that's a pretty awesome problem to conclude. It brings everything together in such a nice way. At this point, I am ready to certify you as a factoring master. You know how to use the box. You know how to guess and check. You know how to factor when a is 1. You know a difference of squares. You know a perfect square trinomial. So your next class, you'll have some review going on, and then we'll test just to make sure that you can demonstrate that knowledge and that you feel confident on this fairly tricky concept. Thanks for hanging out with me. We only have 2 units left in algebra this year, and they're both going to relate to things we've done so far. I think there's a lot less learning, and the units are a lot shorter. So get some rest, get some practice in, and I'm excited to have you back for topic 9.